Okay, so in the last lecture, we started looking at something called the definite integral, and we said that this definite integral was just a renaming of what we looked at previously. So if you want to find the area under a curve from A to B, you can use that limit definition, and then we renamed that, or we gave a new notation with this thing over here. We call that the definite integral. So the area from A to B, that's given by this object here. So at the bottom we have A, that's our lower bound. At the top we have B, that's the upper bound, so that's the endpoints of the interval. Inside here, that's the function, and then here we put the differential dx. That took the place of the delta x from the limit definition. Okay, so far we've been evaluating this using the limit of a Riemann sum, okay, exactly the same as what we did for the area. Next week, we're going to be doing the fundamental theorem of calculus, and with that, we'll see that there's a much easier way to calculate these. Yeah, but for now, we're still going to be thinking of this in terms of the areas. So when proving these different properties, we'll be doing it in terms of the areas. Okay. Later on, when we do the fundamental theorem of calculus, we will go back and prove these again using the new way, okay, which is a bit better. Okay, but you should always keep both ways in mind as we're going through this. So, lecture. We're on 16, sorry. Okay, so we looked at two properties previously in terms of the sum definition. Now we're going to look at the rest of them. Okay, so we'll start with the first two and then we'll add on the rest. So, number one, we have the integral from A to B, f of x plus or minus g of x dx. Now we know that this integral, that's just a fancy sum. So in sums, we can separate things into two parts, like we did with the limit case. Here we can also separate things into two parts. So here we have the integral from A to B, f of x dx as the first bit, like the first sum, plus or minus the integral from A to B, g of x dx. That's the second bit, like we had before. So remember when we had the sum of I and the sum of r squared and the sum of r cubed, we separated them out. We can do the same thing here, so we can separate these out. Okay, property number two, if we have the integral from A to B, some constant k times f of x dx. Again, this is a fancy sum, so if we have a constant inside, we could take the constant out of the sum. We can also take the constant out of the integral. So it will be k times the integral from A to B, f of x dx. Okay, so those were quite easy to see from the sum definition. Now the rest of them are a bit more tricky, but not so bad. So number three, we have the integral from A to A, f of x dx is equal to. Now here we can imagine this in terms of an area. So if we're going from A and we're ending at A, we haven't moved anywhere. So the total area underneath that curve is going to be 0, right? Because the rectangle has 0 width. We started at A, we ended at A, that's going to be 0. Okay. If you were to show this using that sum definition, remember how we define that delta x. It's the upper bound minus the lower bound divided by n. If the upper bound is a and the lower bound is a, you take the difference at 0. So your delta x is 0, which makes everything 0. Okay, number four, the integral from A to B, f of x dx is equal to minus the integral from B to A, f of x dx. Okay, so here If we're going from A to B in like the positive direction, if you want to think about it like that, we get this answer on the left-hand side. If we swap the bounds and we now go in the opposite direction, we pick up a minus sign. So going from A to B, that's plus. Going from B to A, that's minus. A quick way to see why that is true. If we got some function here from A to B, remember how we defined the delta x? It's B minus A over N. So here we get delta x is B minus A over N. Now, if we go in the opposite direction, it will be A minus B over N. So here delta x will be A minus B over N. But we can just take out a minus sign, and we get B minus A over N. But that's the, let's put a little prime there, but that's minus delta x. Okay, and if we have a minus delta x, that minus goes out to the front like we have over here. Okay, so if you have the integral from 1 to 3, it's minus the integral from 3 to 1. Okay, next one, number 5. If f is an even function, okay, is anybody not familiar with even functions and odd functions? Okay, so if f is an even function, then the integral from minus a to a, f of x dx, is equal to twice the integral from 0 to a, f of x dx. Okay, so we can see this is true with the little picture of an even function. So let's just say we have a parabola. That's like the simplest even function. Okay, we want to go from here to here, from minus a to a. We know that it's symmetric because it's even. So what we have on the left-hand side is the same as what we have on the right-hand side. So if we want the total area, let's just calculate what's on the right-hand side and double it. Okay, because it's the same as what's on the left. Okay, so that's if it's an even function. If it's an odd function, so if f is an odd function, then the integral from minus a to a, f of x dx, is equal to 0. Okay, so why is that the case? It's because whatever's on the right-hand side is mirrored on the left-hand side, but inverted. So if you want to think about this in terms of like a cubic, it looks something like this. Okay? Now, if we want to go from minus a to a again, from minus a to a, something like that. On the right-hand side, we've got a positive area, whatever that may be. On the left-hand side, we have a negative area. Remember, we went through this before. If the area is below the x-axis, it comes with the minus sign. So on the left-hand side, we have some area with the minus sign. On the right-hand side, we have the same area, but with the plus sign. If we add the two together, we get 0. So if we have a symmetric domain, so from minus a to a, of an odd function, then the result is 0. Okay, one more property that we'll be using. If we have the integral from a to c, f of x dx, this is equal to the integral from a to b, f of x dx, plus the integral from b to c, f of x dx. Okay, so over here, we've got a single function, and we're separating it out. The way we're separating it out is based on these bounds here. So this b lies somewhere between a and c. So we'll show a little picture. Okay, got a little picture here. So here's a, here's b, here's c. So if we look at the total area under the curve, so let's just draw that in green. So we've got this part in green and this part in red. Okay, so we've got this green part and this red part. So the green part we can identify with this first bit. That's the green part. And then the red part we can identify with that bit. On the left-hand side here, we have from A to C. That is the total area. So from A to C, that's all of it. On the right-hand side there, we've got the green part plus the red part. Again, that's the total area. So here, whenever we have bounds from something to something, we can always split it up with another bound that lies between them. Yeah, and you can do this multiple times. You can split this up into 2 parts, you can do it into 4 parts, as many parts as you need to answer the question. Okay. Any questions on this? Okay, no questions. Okay, so let's go over those homework problems, and then we'll look at the proofs for these as well. Okay, so the first one was the integral from a to b, f of x, plus minus g. Okay, and we want to show that we can split this up. So that's the integral from a to b, f of x dx, plus minus the integral from a to b, g of x dx. Okay, so we want to prove this. So we're going to prove this using the limit definition, so the limit of a Riemann sum. So we'll start off with the left-hand side and then try to get to the right-hand side. Okay, so standard proof. Okay, so we have the integral from a to b, f of x plus minus g of x dx. Okay, now we're just going to use the definition that we know. So this is going to be the limit as n goes to infinity, the sum from I equals 1 to n. Then we're going to have f of xr plus minus g of xr delta x. Okay, so we've got that. Now, ignoring the limit for a bit, look on the inside part here. So we have the sum from I equals 1 to n. That's a finite sum. So since it's a finite sum, we can do a bit of rearranging. So we're going to have the sum of the first term plus minus the sum of the second. So it's a finite sum, we have no issues there. So here we have the limit as n goes to infinity. We have the sum I equals 1 to n, f of xr delta x, plus minus the sum I equals 1 to n, g of xr delta x. Okay, now all of this is still in the limit. Okay, so we're just working with that sum. Now we've got the limit and we've got 2 things inside here. What we would like to do is take the limit of the first thing plus or minus the limit of the second thing. Now remember back to your limit laws. If you have the limit of something plus or minus something else, if you want to separate it, these individual limits need to exist. Okay, that's the only way that we can separate limits. So how do we know that these exist? Well, if we look back here, if we separate it, we expect that to get this bit here and this bit here. Okay, so we're going to assume that those 2 limits exist. If they don't exist, then we couldn't have done this in the first place. Okay, so we can safely assume that those limits exist. Okay, so since the limits exist, we can separate them out. So here we have the limit, n goes to infinity of the first one. We know the limits exist, so everything's fine. I equals 1 to n, f of xr delta x, plus or minus the limit as n goes to infinity, the sum I equals 1 to n, g of xr delta x. Okay, so we separated that out. Okay, and we know the reason. Now, if we look at the first term, this is just the definition for the definite integral, and the same for the second term. But the first one, we have the function f, the second one, we have the function g. So just by using the definition, we can write this as the integral from a to b, f of x dx, plus minus the integral from a to b, g of x dx. Okay, so those are all the steps that we need. Okay, please make sure you understand each of the steps properly and the reasons for each of the steps. So if I ask you this in the test coming up, you should be able to provide the reasons for why you're doing each of the steps. Okay, let's have a look at the second one. So here we had the integral from a to b, k times f of x dx, and we said that we could take the k out of the integral. So that's going to be k times the integral from a to b, f of x dx. Okay, so how do we prove something like this? Again, we go back to the definition. So the integral from a to b, f of x dx, we know what this means. We can write it as that limit of the Riemann sum. So this will be the limit as n goes to infinity, the sum from I equals 1 to n, k times, sorry, there's a k there, k times f of xr delta x. Okay, so we just use the definition. Okay, so now if we look inside the sum here, we've got this k times f of xr, but the k is a constant, and here we have a finite sum. If we have a finite sum, we can use our sigma notation properties, and we can take the k outside of the sum. So here we have the limits. As n goes to infinity, we can take the k outside of the sum, I equals 1 to n, f of xr delta x. Okay, so the reason for this was that we have a finite sum and we can take the constant out. Okay, don't do too many things on one line, or else you're going to have multiple reasons for why you did that. Okay, now we've got a k inside here and something else, and we've got the limit as n goes to infinity. Now this k has nothing to do with n, it's just a constant. So again, we can use our limit laws. If we've got the limit as n goes to infinity of a constant times something, we can take the constant out of the limit. Okay, that's just one of our limit laws. If you don't know your limit laws or you forgot them from last semester, please go over them again. Okay, you will need to know them for these proofs. So we can take the k out, and then we have the limit as n goes to infinity, the sum I equals 1 to n, f of xr delta x. Okay, so now this last line looks like what we want. That limit as n goes to infinity of all of that, that's just the definition of a definite integral. So we can replace this with that integral, and we have the k outside. So we have k times the integral from a to b, f of x dx. Okay, are there any questions about this? Okay, so no questions about this, so we can move on, everyone's happy. Okay, if you stay silent, I'll just assume you know what's going on, and then we're going to move forward. Okay, so the way that we do these proofs is very similar to how we do those other proofs. So here, if we go back here, okay, so we've done this one, and we've done this one. Okay, so this one over here from a to a, I discussed that already. If you have delta x with the same upper bound and lower bound, it's going to be a minus a over n, so we get 0. So you can write that out properly. So that one's done. Number 4, so with this one, just by looking at the picture, we can see what's going on there. But here on the right side, we see that if we do swap the bounds, the new delta x, the delta x prime, is minus the original. So the minus comes out, and that's why we get this minus sign here. Okay, so I'll leave that for homework to write it out fully. Okay, and then over here for number 5, so we just drew the picture to explain how this works, but you can do the full working for that. Okay, so that will be another homework problem. The same thing with the odd function. Okay, so number 6, I'll do the proof, and then you can do those other ones for homework. Okay, number 6, we have the integral from a to c, f of x dx is equal to the integral from a to b, f of x dx, plus the integral from b to c, f of x dx. Okay, so for this one, we're going to do the same type of proof as before. We start with the definition, we do a bit of manipulation, and then we go back to what we want. So let's start off with the left-hand side. We have the integral from a to c, f of x dx. We can write this out using the definition. Okay, we know what that is. So that's going to be the limit as n goes to infinity. We have the sum from I equals 1 to n, f of x r delta x. Okay, so that's just using the definition. We've done this many times now. So what we want to do is separate the bounds into these two parts. So we've got this big interval from a to c. We want to split it up into the sub-interval from a to b, and then from b to c. So in terms of a picture, what we've got is something like this. So we've got A, we've got C, and then we've got all these rectangles over here. Okay, so what we want to do is find somewhere in between. We're going to call that B. We're going to split the sum into two parts. We're going to have the sum up to where B is, and then the sum from B up to C. So inside the limit, the sum here, we're going to split into 2 bits. So here we have the limit as n goes to infinity, the sum from I equals 1 to, let's say, m. Okay, so m is somewhere in between. So let's say over there. Okay, plus the sum from m, I equals m, m to n, f of x r delta x. Okay, now m here, that's just a constant. That is the position of whatever that middle rectangle will be, wherever this b should be. Okay, so we've got the limit as n goes to infinity, and then again, all of this here, that is inside the limit. So what we want to do now is separate this into 2 parts. We're going to have the limit for the first part, and we're going to write that as the first definite integral. We're going to have the limit of the second part, and we're going to write that as the second definite integral. Okay, so we have the limit as n goes to infinity, the sum from I equals 1 to n. I'll put a little star here, we're going to get back to this. F of x r delta x, plus the limit as n goes to infinity, the sum from I equals m to n, so that's the rest of the rectangles, f of x r delta x. Okay, and I put a little star there. Okay, there's a problem with this line. So we separated the limit into 2 parts. So here we've got the limit for the first bit, we've got the limit for the second bit, but there's something wrong here. Okay, can anyone see what's wrong? Yep. Sorry, too much noise in the computer. Yeah, so we got it. So here for the first one, we have the sum from I equals 1 to m. We got this m here. But we're still taking the limit as n goes to infinity. So there's a problem with that. over here, we've got the limit as n goes to infinity. Here we're starting at n, and we're ending at n. So there's a problem there. Okay, so what we want to do is do a little bit of manipulation here, so that this first one looks like a definite integral, and the second one looks like a definite integral. Okay, so I'll just draw a picture again, and then we can see what to do. Okay, so we've got our A, B, and C. Okay, we've got our rectangles here. So here at the beginning, I is equal to 1. I is equal to m. I is equal to n. Okay, so we've got this bunch of rectangles there. Okay, so we've got a problem with that first limit there. Okay, so we got from 1 to m. Let's go up a bit. Okay, we've got from 1 to m. M over there lies between the two. And then the second one starts from m and ends at n. So that bit's fine. Okay, so what can we do with this first one to make it look more like what we want? Okay, any ideas? Yep. Yeah, good. Okay, extra points as well. Okay, good. So here, this m, we're going to treat this first part from here to here as its own integral, and then from here to here, we're going to treat it also as its own integral. So we're going to split it up like that. So here, when we have the sum from I equals 1 to m, that m we need to treat like the n we used for the original definition. Okay. Okay, good. So you should be on 4 points. Just see me afterwards. Okay. So we have the limit m goes to infinity, and then we can change the delta x, right? That's just a constant. So instead of going from a to c over n, now we're going from a to b over m. Okay, just a little bit of rearranging there. So this will be the sum from I equals 1 to m, f of x r delta x. We can put a little prime there, but we know what we did. So that delta x prime is going to be b minus a over m, right? Because it's a new one that we're doing. Plus the limit as n goes to infinity. We can keep n, or you can change it to something else. N goes to infinity. The sum from I equals 1 to n now, f of x r delta x, let's put a double prime. So that's going to be c minus b over, so here we're writing it as n, or you can put a different letter. Let's do something else. Let's see. Let's call it p. Get rid of that. So we can call it p over there. So that's from 1 to p. And then that leftover bit over there. So if we're going to call this 1 now, p will be n minus m. That will be the leftover bit. Okay, so that's going from m to n. We're just renaming it to p and going from 1 to p. Okay, we're just shifting everything down. So instead of starting from m and ending at n, we shift everything down. We now start from 1 and we end at p. Anyone confused with that? Okay, I'm not seeing any hands, so let's carry on. So now the first bit, we did a bit of rearranging, but it's still a definite integral, right? It has the same limit definition. So we have the integral from a to b, right? We did a bit of changing there, so the bounds will change. A to b, f of x dx, plus the integral, and again, we did a bit of changing. So now, instead of going from a to c, we're going from B to C, because we did that shifting. So this goes from B to C, f of x dx. Okay. So the redefinition for delta x and delta x prime, just make notes of that on the side. Okay, so we need to change that because the first section, we're not having n triangles, we're having m triangles. And for the second section, we're not having n triangles anymore, we're having n minus m triangles. Rectangles, sorry. That's for the right side. Okay, any questions on that? Yes? The P. So P is how many how many rectangles we have left here. So when going from I equals m to n, we're going to change that. So I'll just make a note here. So I equals 1, I equals, m to n. So we're starting from m and we're going to n. But for the definition that we want to start from 1. So we're going to take this sequence here from m to n, and we're going to shift it. So for each of these, we're going to minus m minus 1, minus m minus 1. So now we can call it a new letter if you want. We can call it j. So j will now go from 1 to j equals n minus m plus 1. That n minus m plus 1 we call p. It's just the result after shifting everything down. So here m, we started with m, we shifted to 1. We started at n, we shifted to this number, but we're just calling it p. Okay, good? Okay, so it's just calling it a different name. So we just shifted it down and then called it a different name there. So over here, if it is a bit confusing, you can call this j if you want to. You can put the j there. That's fine as well, right? It's just the letter that we're using in the sum. So going from the previous one where we used I, if you want to change it to j because we're doing something different, that's fine as well. You can do that. Or you can keep it as R. Okay, any other questions with that? Okay, so those other proofs, I'll leave that for homework. Okay, so that will be due the next Monday. Okay, I hope everyone has been submitting their homework. I did get quite a lot of emails, so I haven't counted them yet, but I think it's most of the class. Okay, so the homework, I'll just write it out again. So that's the integral from a to a, f of x dx is equal to 0. So I went over all the explanation, you just need to write it out neatly. Okay, then the integral from minus a to a, f of x dx is equal to twice the integral from 0 to a, f of x dx if it's even. And then the integral from minus a to a, f of x dx is equal to 0 if it is odd. Okay, so we did go through all of that, just write it out neatly. You can hand it to me in my office or email. Okay. But if you do have any questions, just in the email when you're sending it to me, just say, please check my work, or please explain something, or if you just want to submit, you can just leave it blank. Okay. Any questions before we move on? Okay, so everyone's okay with these properties and how to prove them? Okay, please, if you have any questions, put your hand up and I'll go through it. Nothing. Okay. Okay, so I will introduce the next topic on the fundamental theorem of calculus. So I'll go through it briefly now, just so that you can use it when doing the tutorial work. So for now, the tutorials, you're going to be doing it using the limit definition, so the limit of the Riemann sum. However, with this new technique, you can check your work very quickly. Okay. So if you do put that in your tutorial work when you submit it, I can give you some points as well. Okay. So whenever there's a chance to give points, I'll give points. So please just make use of it. Okay, so the fundamental theorem of calculus. Okay. Now, the fundamental theorem of calculus comes in two parts. So there's FTC, as we say, part 1, and FTC part 2. Now, different textbooks and YouTubers and wherever you're looking up the notes, they might swap them around. Okay, so it's not a standard for which part is which. Okay, so just keep that in mind. If I'll show you part 1 here and it looks different to a part 1 you see online, they could have just swapped part 1 and part 2. Okay, so please just keep that in mind. Okay, so let's have a look at part 1. Okay, so I'll just introduce it, and then you can use this to check your work. And again, if you submit your tutorial and you show the limit of a Riemann sum way, and you also show this way, I can give you extra marks for each of those. Okay. And that's per student, right? It's not like the first person. It's not like the homework. Okay, so anyone that does it both ways, you'll get the points for that. Okay, so part 1. So we have the integral from a to b, f of x dx. Okay, so we have this thing again. So now we know one way of calculating this. We do the limit of the Riemann sum, we take the limit, simplify, do all of that, we get our answer. Okay, it's quite a long way. There is an easier way to do it, and that comes from this FTC part 1. So the way that we calculate this is equal to capital F of B minus capital F at A, where this capital F of X is any antiderivative of F. Okay, the little f. So remember back when I said the antiderivatives will come back again, this is where we're going to be using them. Okay. Now, remember when we did antiderivatives, we said that the antiderivative was not unique. It was always a capital F of x plus c, and we always had the plus c for it. Now, that plus c could be any constant, right? Which means we have infinitely many antiderivatives. So, if we have infinitely many to choose from, how can we pick one to calculate this? The nice thing is, it doesn't matter which one we pick. Okay, and we'll show that here. The choice of antiderivative doesn't matter. Okay, so you can pick any constant c, it makes no difference to this. The proof is very easy. So we have the integral from a to b, f of x dx is equal to, so any antiderivative evaluated at b, so let's put any one, so that's f at b plus c. The plus c means it's any of them. Minus, again, any antiderivative at a. Now you can't choose two different ones, they have to be the same. So we're going to have capital F at A plus C. Yeah, the C I'm leaving to be anything. So this first bracket, that's again, any antiderivative, same thing with the second. Now, why does it not matter? Can anyone see quickly? Yeah. Yeah, exactly. Okay, again, see me after, I'll give you some points for that. So yeah, it will cancel out. So let's just expand out these brackets. We're going to get FB plus C minus FA, and then the minus also goes on to the C, so minus C. But the plus C and the minus C, they cancel, as you said there, so that goes away, and we're left with FB minus F at A. Okay, so if we chose any constant C, doesn't matter what it is, in the next line it automatically goes away. Okay, so that means it doesn't matter. So when we're doing these, it's best to just choose C to be 0, right? We could choose it to be anything, but for simplicity, especially over here, for this bit, let's just choose it to be 0, because why not? Okay. So we are free to choose C to be equal to 0. Okay. You can choose something else if you want, but you'll see when we're doing these calculations, it's best to follow this. Okay, so let's have a look at an example. We're going to do this problem 2 ways, and we'll see that hopefully we get the same answer. So we're going to calculate the integral from 0 to 1 of x squared dx 2 ways. Okay, we're going to calculate it using the limit of a Riemann sum. Okay, again, that's for this week's tutorial work. And then we're going to calculate it using this FTC part 1. That should be next week's tutorial work. But again, if you want to do it for this week's to get some extra points, please do that. Okay, so first way, limit of a Riemann sum. Delta x is going to be 1 over n. Xi is going to be I over n. And f of xi is going to be r squared over n squared. Okay. If you do need me to slow down to go over this from previous work, please just let me know. I'll slow down, but this should be quite easy to do. Okay, so let's put everything together. We have the limit as n goes to infinity, the sum from I equals 1 to n, f of xr delta x. Okay, so everyone should have that memorized by now. So this is the limit as n goes to infinity, the sum from I equals 1 to n. We don't need brackets for that. F of xi will be this r squared over n squared. And then the delta x, that's 1 over n. Okay, so just a note on that. I went through those homework submissions on this stuff. A lot of students were leaving out this delta x. If you leave out the delta x, you end up getting infinite answers. Okay, so if you do go through your work and you see you're getting infinite answers, just go back up a few lines and see if you included that delta x or not. Okay, that might be the reason for your infinite answers. So here we have the limits as n goes to infinity, the 1 over n and the 1 over n squared, there'll be 1 over n cubed, we can take that out. Then we have the sum from I equals 1 to n r squared. Okay, now we've got it in that nice form, we can just replace it. We know what to do. So that will be the limit as n goes to infinity, 1 over n cubed, n times n plus 1, 2n plus 1, all over 6. Okay, again, after doing the tutorial work, that should be memorized as well. Okay. Few examples and then it's quite easy to remember it. Okay, we can cancel the n at the top and the n cubed at the bottom. That will be an n squared at the bottom. So we're going to have the limit as n goes to infinity, the 1 over 6, let's put that here. Then we have n plus 1, 2n plus 1, all over n squared. So we have the n squared now. Okay, now we have the limit as n goes to infinity, 1 over 6. Expanding this out, we get 2n squared plus 3n plus 1. Again, if you do this enough times, going from that bracket to there, it's kind of just muscle memory at that point, right? So you don't really need to think about it. Okay, over n squared. Okay, like I said before, we've got multiple numerators, a single denominator. We can split that up. So this will be the limit as n goes to infinity, 1 over 6. 2n squared over n squared, that will just be a 2. Here we get a 3 over n, and the other one we get 1 over n squared. Okay, now we take the limit. It's as easy as just crossing out these terms. So we get 2 over 6, or 1 over 3. Okay, that took quite a while to do. Many steps, a lot of places where we could have gone wrong. Let's check our answer using this new FTC part 1 that we've learned. Okay, integral from 0 to 1, x squared dx. This is going to be equal to a little bit of notation here. So the way that we write the f at b minus the f at a, we usually write it like this. So we have square brackets, and then inside we put the antiderivative. Would anyone like to answer that? Yes? Perfect. 6 points so far. Well done. So 1 over 3 x to the 3. We put the antiderivatives in the square brackets. We should have had a plus c, but I chose it to be 0. Now, when doing the work, you don't need to say you chose it to be 0. You can just leave it out. Okay, I know what you're doing. Okay, then we have the lower bound we put at the bottom, and the upper bound we put at the top. Okay, this is just notation for the work, right? It's not so important for the calculation, but it allows us to see what we're doing. Now what we can do is what we had at before, the capital F at the top one minus the capital F at the bottom one. Inside the square brackets there, that's our capital F. So it's going to be 1 over 3, 1 cubed minus 1 over 3, 0 cubed. Now the 1 cubed, that's 1, 0 cubed, that's 0. We get 1/3. Okay, and we get the same answer. So you see how much easier it is to use this FTC part 1 instead of doing all of that other stuff. Okay, so again, for the tutorials, please do the limit definition. Okay, so just to test that. However, for the test that's coming up, there's going to be one question on the limit way. The rest of it, please use FTC 1. Okay. Okay, so just one question on that top bit, just to check that you know what to do. But everything else from then onwards, please use this much better method here. Okay. Again, in the test, for the method where you do the top one, if you want to check your answer, you can do that as well. So you can do the long limit way, check your answer, and then compare to see if you get it right. Okay. If both of them match up, then that's almost guaranteed you got it correct. Okay. Any questions on this FTC 1? Okay. So this was just a quick introduction, just so you know what to do. So for the tutorials, you can do this. Next week, we will go through it properly. We'll look at the proof and with more examples. Okay, but for those of you that want some extra points, here's some homework problems. Okay, let's give you 5. So if you do all 5, you get 10 points. So I mean, that's pretty nice. Yeah, just with the point system, for the previous test, one student did go from a B to an A with their points. I don't remember who, but there was one. They got a B with the test, and then it got bumped up to an A. So, I mean, the points do work, right, if you're going from a B to an A. I don't know if it was this class or another class, one student failed the test, and then it got moved to a passing mark, again with the points. I don't know which class it was. One of the classes got that. Okay, so I mean the points do work. You can see. Okay, so integral from -1 to 1, x to the 100 dx. Okay, try to do that with the other method. You'll be here all day. Okay, integral from 0 to 2, x squared plus a quarter x cubed plus 1. Integral from 0 to pi, sec squared x plus 1 over x dx. Integral from 0 to 1 plus x squared dx. 1, 2, 3, 4. Last one, integral from 0 to 3, 3x plus 2x squared plus x dx. Okay, 5 of them, pretty easy. Please don't try doing it the other method, use the FTC one. So for these ones here with the quadratics and cubics, you could do it both ways. It's not so difficult. The one with the sec squared and the 1 over x, don't even try doing it with the limit way. Okay, it's far too much work. Okay, but with the sec squared and the 1 over x, you can easily do that using the FTC one. Okay. So there's 5 of them, 2 points each. Yeah. Par. Yeah, from 0 to par. Over here. 0 to 1. Yeah, sorry. Let me try zoom in there. Okay, I'll go over it again if you can't see. So number 1 is the integral from -1 to 1, x to the 100 dx. Number 2, the integral from 0 to 2, x squared plus 1 quarter x cubed plus 1 dx. Number 3, the integral from 0 to pi, sec squared x plus 1 over x dx. Remember 1 over x, that was that special case we talked about. Number 4, the integral from 0 to 1, 1 plus x squared dx. And the last one, the integral from 0 to 3, 3x plus 2x squared, that's a 2, sorry, plus x dx. Okay. Same rules as always. First person to submit will get the marks, provided it's correct. Okay. So you do have until Monday, as with the other homework problems, but try submit today. I've seen students submitting right after the lesson. Okay, that happened on Monday. A student came up to me afterwards and gave the homework for that day. Okay, so be quick with those. All right, any questions on this? Okay, any questions on previous stuff that we covered? Okay, please don't feel embarrassed to ask questions. If you are confused with something, please just let me know. Or if you do want to tell me privately afterwards, if you think it's a silly question, you can do that as well. Okay. Okay, last chance, any questions? Okay, yeah, if you do have anything afterwards, please just come and see me.